Hello everyone, my name is Osama Shahid. I will be presenting Cloud-LoRa, which enables cloud radio access LoRa networks using reinforcement learning based dynamic compression. It's a joint work with Krishna Chintalapudi, Professor Suman Banerjee, and my advisor, Professor Bhuvana Krishnaswamy. LPWANs, low power wide area networks, have been an emerging set of networks that address the needs for large scale IoT devices. Some of the predominant applications that drive the need for these LPWANs have been smart agriculture, smart city, and smart meters, where hundreds of devices are connected to the cloud server. Some of the common needs for these LPWANs are wide area coverage, large scale, while consuming as much low power as possible. Scaling such sort of LPWANs have been a recent challenge where the number of end devices have been increasing and gateways are not able to serve all the end devices. To address this scalability issue, recent LPWAN technologies have resorted to multi-gateway solutions as well as leveraging cloud resources. Let me give you an example of LoRaWAN, which is a popular LPWAN technology. In LoRaWAN, end devices send their wireless messages to the gateways. Multiple gateways can listen to the same message. The gateways send these messages to a cloud server where redundancy is used to decode bits. Some recent works have mentioned that by increasing the number of gateways, we can improve the scalability of LPWANs. Just like this work on the right plot shows that by increasing the number of gateways, we can incorporate more number of end devices in the network. Increasing the number of gateways is helpful, but we can't keep on doing that because one, the gateways are expensive. And second, it defeats the purpose of LPWANs, that is long-range communication. Similarly, some of the recent works like Nifalai and Charm mention using cloud radio access networks to improve the scalability of LPWANs. Let me spend some time on explaining what a cloud radio access network is. In traditional networks, the gateways they receive raw IQ samples and then perform all the physical processing at the gateways and send the decoded bits up in the cloud. As opposed to that sort of networks, in cloud radio access networks, or CRAN in short, the gateways are dumb devices. They just capture raw IQ samples from as the messages, the end devices send the messages and the gateways capture them as raw IQ samples. These raw IQ samples are simply compressed and sent up in the cloud via internet backhaul. And in the cloud, all the processing, including physical layer processing, is performed. I want to mention that this CRAN as an architecture is not something that is new. It is already deployed for cellular networks, and it offers a lot of benefits. One, since cloud has this global view, in the cloud, users can coherently combine raw IQ samples in order to improve the SNR and therefore improve the range of communication. Moreover, the local gateways have limited compute capacity. In the cloud, we don't have this constraint. Therefore, in the cloud, we can elastically scale to multiple channels, therefore improving the scale of the network. And also, CRANs help us to deploy physical layer innovations very quickly. I want to mention that in traditional networks where CRANs are deployed for cellular, the backhaul that connects gateways to the cloud is fiber optic backhaul, whereas LPWANs are deployed in remote locations where fiber optic backhaul is not available, and what we are left with is mostly cellular backhaul. To give you some perspective of what this practical challenge looks like, we deployed CRAN gateways at different locations within a vicinity. This was a remote farm in Wisconsin within an area of 2.4 kilometer by 3 kilometer. And at different locations, we measured how the backhaul bandwidth looked like. At location 1, we observed the backhaul bandwidth to be around 2 megabits per second, which is extremely low to relay raw IQ samples up in the cloud. Similarly, at locations 2 and location 3, we had low backhaul bandwidth, and also, as you can observe, there are significant variations in the backhaul bandwidth based upon the gateway location. The connection was intermittent, and at many times of the day, we didn't even have connectivity. So even though CRANs have its own advantages, but realizing those advantages for LPWANs is challenging due to the limited backhaul bandwidth that is available. To address this issue, we propose Cloud-LoRa, which is a practical CRAN for LoRaWAN. Cloud-LoRa consists of 3 main blocks: channelization, activity detection, and reinforcement learning. The first is channelization block, which takes raw IQ samples from a CRAN gateway, which for our case is a USRP B200 software-defined radio. This channelization block takes all the raw IQ samples and channelizes them using lightweight filters. And all these channels are then passed on to activity detection block. So this activity detection block is continuously listening onto the incoming raw IQ samples. And whenever it sees activity in the channel, it isolates it from noise samples in what we call as active periods. As I mentioned, already the backhaul is very limited. We don't want to send noise samples. So therefore, activity detection block is critical in identifying where all the activity lies. So all these active periods are then fed to a reinforcement learning-based dynamic compression block that dynamically compresses the incoming radio samples based upon the available backhaul. Channelization block and activity detection block, both of these are, a lot of signal processing is going on. And for today's talk, I will be presenting reinforcement learning-based dynamic compression block. So before designing such an dynamic compression algorithm, we asked a question, that is, how does the state-of-the-art compression techniques perform? We looked at static lossless compression, in which there is gzip, LZ4, and LZW. They give somewhat around 60% compression score, but that is not enough to meet the limited backhaul that we just saw. Some recent works like SPAR-SDR and NFLi propose static lossy compressions. One, they are not able to meet the limited backhaul bandwidth, and also they don't adapt to the varying backhaul bandwidths that we just saw. We might use supervised learning-based algorithms like SVM or linear regression to dynamically compress the incoming radio samples. But again, there is an issue that these require a lot of data set for prior training before they can be deployed out in the wild. And also, not all of them work in real time. So therefore, in order to meet limited backhaul bandwidth and in order to adapt to varying backhaul bandwidth, we propose reinforcement learning-based dynamic compression, which does not require prior training and also runs in real time. Reinforcement learning falls under unsupervised learning, where there is an RL agent. It observes the environment using some state variables. It performs sample action, which creates some change in the environment. It gets some feedback, and based off of that, it updates its policy function so that it can perform future actions that can lead to more rewards. We call our dynamic compression block ACIO. ACIO has a DWT compression block. DWT is for discrete wavelet transform, which is quite popular for image processing. I want to mention that this compression block can be replaced by other compression algorithms as well. And controlling this block is an RL agent, which is PPO, proximal policy optimization algorithm. ACIO runs on a laptop. And as I just mentioned, there is an activity detection block, which is continuously listening onto the incoming radio samples. And whenever there is an activity, it isolates it from the noise samples into what we call as an active period. Those active periods are fed to ACIO. ACIO observes the environment and compresses it. And as TCP packets, it sends all these samples to the cloud server via internet backhaul. In the cloud, signal is reconstructed, decoded, and a reward is computed, which is sent back to an RL agent in this feedback loop, and RL updates its policy. There are three main components for RL agent. One is state variable, action set, and reward function, which defines how RL will perform while it is learning on the go. For ACIO, state variables are either LoRa characteristics-based state variables or network characteristics-based state variables. Under LoRa characteristics-based state variables, we have length of incoming active period as one of them, and SNR of the active period, and also some other statistics of received signal strength as some of the state variables. Under network-based state variables, we have bandwidth observed, a history of bandwidth observed, and measured latency as some of the state variables. I want to mention that we observed the bandwidth and measured the latency using network statistic tools of TCP BBR. These state variables are fed to RL agent, which observes the environment using these state variables and then takes an appropriate action. For ACIO, action is choosing an appropriate level of DWT compression. ACIO can choose an action from a discrete set of 0, 0.1, 0.2 all the way till 1. An action of 0 would mean there is 0 compression, and an action of 1 would mean there is maximum compression. Once an action is taken, the incoming raw IQ samples are compressed and then sent in the cloud where it is reconstructed, decoded, and a reward is computed. So the third key component of this RL agent is reward function. To shape a reward function, shaping any reward function is determined by the goals of the system. And the goal of our system is to maximize number of packets that are decoded in the cloud. Therefore, whenever a packet is decoded in the cloud, we reward positively. We also want to meet the available bandwidth as well as be within latency constraints. Therefore, whenever these two things are not met, we add a negative reward to our whole reward function. So this plot shows how we shape corresponding to latency. So on the x-axis, we have latency ratio, which is measured latency divided by some preset limit. Whenever this ratio gets close to 1, we start adding a negative reward. Similarly, for bandwidth, there is a bandwidth ratio, which is the ratio of utilized bandwidth to the available bandwidth. Whenever this ratio also gets close to 1, we start to add negative penalty. And finally, for number of packets decoded, we have a positive reward, which is scaled by the number of packets decoded. There is some more detail to it, which can be found in the paper on how we shape our reward function. Putting it all together in a pipeline, we have an RF front end that gives out raw IQ samples that are fed to channelization block, which converts into multiple channels. These channels are fed to activity detection block, which isolates activity from the noise samples into what we call as active periods. These are then fed to an RL agent, our Accio dynamic compression block. Based upon the environment, it observes how the incoming active periods look like, and it also observes how the backhaul bandwidth looks like. Based off of that, it compresses the incoming samples and sends it up in the cloud. We implement cloud server in Microsoft Azure. All these TCP packets are sent to a multiplexer in the cloud, which first decompresses the incoming packets, and then using some metadata in the packets, it assigns each of the packet to a consumer container. For each channel, we have a separate consumer container, which runs LoRa decoder as a Docker container. From all these containers, packets are decoded and then are again collected by this multiplexer, which computes reward and sends it back to the RL agent, which again updates its policy function. So I want to mention that whole implementation of ours it runs in real time, and it can be found at the GitHub link at the bottom. So we wanted to have a real deployment, CRAN deployment for LPWAN. Therefore, in our evaluation section, we actually deployed our whole system in a remote rural deployment in a 2.4 kilometer by 3 kilometer region. It was an agricultural land where we distributed 8 LoRa nodes out in the field, and each LoRa node transmitted in a unique channel. We had USRP 200, B200 as our base station. It streamed live samples to a client laptop on which we were running active periods, activity detection, as well as our Accio algorithm, which dynamically compresses. So as I mentioned, our cloud server implementation is in Azure server. We left it out in the field for multiple days and collected the results. In this slide, I'll be mentioning some of the results that we see. In this plot, we have overall throughput observed against varying backhaul bandwidths. The green bar shows the Cloud-LoRa. We also compare our result against some other static lossy compressions, for example, Nepali and SPAR-SDR shown by orange and red bars. Then there is rate-limiting oracle as well, which sets some upper bound. We assume that this rate-limiting oracle has a global view and compresses just exactly to meet the bandwidth. As the backhaul bandwidth increases, we can see that the throughput for Cloud-LoRa increases. The reason for that is that as the backhaul bandwidth increases, the RL algorithm for Accio, it learns to compress gently. This can be validated in this compression score versus backhaul bandwidth plot as well. As the backhaul bandwidth increases, compression score for Cloud-LoRa decreases. Since the compression that is performed by Cloud-LoRa is gentle, in the cloud, the signal reconstruction is of better quality. Therefore, the decoding results are better and results in better throughput as well. Nepali and SPAR-SDR they offer static compression. Therefore, they are not able to keep up with the throughput, and they are not able to compete with Cloud-LoRa. And as you can see, Cloud-LoRa tries to achieve the upper bound limit that is set by rate-limiting oracle as well. One of the goals of Cloud-LoRa was also to adapt to varying backhaul bandwidths as well. So in this experiment, what we did was we changed the backhaul bandwidth from 5 megabits per second to 3 to 1, and then increased from 1 to 3 to 5, and repeated this, So as we change the backhaul bandwidth, we can see that Accio learns in real time to achieve the maximum throughput. You can see there are some sudden dips right at the start. These dips are because of the fact that RL agent has never seen these bandwidths before, and first it learns, and whenever it sees these changes again, it knows what actions it has to take, and therefore achieves maximum throughput. So in conclusion, we present Cloud-LoRa, which is a CRAN, which is a practical CRAN for LPWANs. We propose reinforcement learning-based dynamic compression, which learns based upon the available backhaul and compresses in real time. Our implementation, again, can be found at the GitHub link at the bottom. And with that, I will conclude. If you have any questions, I'd be happy to answer those. Thank you very much.